Oh, yeah, it's good to see you again. Let's dive into Chapter 5, Derivatives and Integrals of Logarithms, Exponential Functions, and Inverses. Very cool stuff. So basically what this chapter is, it's new functions and a review of old concepts that we've already done in calculus. So this is a perfect time to get really, really strong on things like figuring out where a function's increasing or decreasing, points of inflection, concavity, all those things, equations of tangent lines. The only difference? We're going to be dealing with functions like e to the x, natural log of x, other logarithms besides with base e, and other exponential functions besides base e, and even inverse trig functions. So we've got a lot to do, but all of these functions, we're just going to learn about their derivatives and integrals. That's it. No new concepts, just new processes. It's awesome, right? Right, let's keep going. Okay, so that's the general overview of where we're going. So in terms of what we're going to start with, lesson 5.1 is the derivative of y equals the natural log of x. And just to remind you of a few things in natural log of x, that's what we're going to start with in this 10, maybe even upwards of 15-minute video of a real quick breeze through of what the natural log is all about. So I'm just going to review from what you've covered in previous classes before calculus. So first and foremost, the natural log of x is log base e of x. What it essentially means, and I've got that written here too, so I'll put that there. What that means is, a log, just in general, you're saying if y equals ln x, then e to the what? Or e to the y equals x. That's what a logarithm does, right? It inverts an exponential function. So, in other words, the logarithm output, that y value, is an exponent, because you're saying e to the what equals x. All right, here's a graph of the natural log of x. Notice we've got a vertical asymptote here at x equals 0. So the domain of ln of x is all real numbers greater than 0. So that would be x is greater than 0. You could also write it as open parentheses 0 to infinity, right? And that makes sense here because if you plug in any number for the y value, you'll get out the x value, the domain, right? Which is actually the input here. This is just written in exponential form. We can only get out positive numbers when we raise e to a number. And you might be like, wait, what was e again? Quick review. E is roughly 2.72, roughly. It goes on and on forever. It's actually an irrational number. It's beautiful, but it's roughly 2.72. Raise that to any power, you're not going to get 0, but you could get really close to it. The range. Well, the range, if we look at the graph, that would be all the possible y values. That's all the way down to negative infinity. This thing keeps going in both directions, and it does eventually get up to positive infinity. It just goes slowly. So the range is all real numbers. So you could write one of those fancy r's. You could write negative infinity is less than y is less than infinity, or you could write this, negative infinity to infinity. So any one of those work. All right, so that's a brief review there. That's just a little bit of the natural log. Like I said, we're doing a quick flyby. We're going to keep going with a review of the properties of the natural log, or again, ln. So ln of 1 equals 0. That's because this is really saying log base e 1, or e to the what equals 1, and e to the 0 equals 1. E to the ln x is x. Why is that true? Because e and ln undo each other. You're essentially saying with this e to the log base ex. This says e to the what gives me x. E is raising then to that power that gives you x, so it's x. Or you could just say they're inverses of each other, and e and ln undo each other, right? They completely undo each other. Same thing here, it's going to be x. Again, you've got log base ex. What you're saying is e to the what gives me e to the x. E to the x gives me e to the x, or again, ln and e to the something are inverses. They undo each other, leaving us with x. Okay. The three major properties, though, that you really need to know are this, 1, 2, and 3. They're going to come in handy as we get into the calculus of the natural log. So know them well, especially actually know how to go from the right side I'm about to show to the left side. When we add logarithms, we end up with ln of this times that, so ln of ab. That's essentially saying when I add exponents, I end up multiplying the bases. Right? And we'll go over an example now with numbers. So let's say I give you ln of 5 plus the ln of 6. That would be equal to the ln of 5 times 6, or the ln of 30. That's it. This next one, if adding logs, ln of a plus ln of b, the natural logs, results in multiplying those arguments, a and b are known as the arguments, then subtracting will be the division of them, ln of a divided by b. And so here with numbers, like let's say that I give you the ln of, I don't know, 18 minus the ln of 3. That would be equal to the ln of 18 over 3, which is equal to the ln of 6. That's it. Now I actually want you to be able to go from this direction backwards, and we'll go over a couple of those as well in a little bit. This is just going over the general rules. When I've got n, anything, times the natural log of a, or any number times natural log of a, we can write that as ln a to the n. We can do it that way. Okay, why is that the case? It actually makes a lot of sense. What you're doing here when you're multiplying n times ln a, you're basically adding ln a n times. You're just adding it to itself n times. That's what multiplication means. So when I add ln's, I multiply those bases. So that would be ln a multiplied n times. Quick explanations. Again, I'm not going over this to have you be in great shape and understanding why. This is a review of everything that's come in previous classes, right? So 5 ln x is equal to ln x to the 5th. In other words, the whole why behind this, that's prior classes. And in the future, I will get around to rocking a pre-calc class, oh yes, and an Algebra 2 class, and when I get there, you know you'll have the y in there. But for now, we're in calculus. But these properties, know them well. Memorize them if you must. I think you should. Okay, so we're going to actually go through the important part here, which is the expansion of logarithms. And that's going to be important when we take derivatives of these things, because as you can imagine, whatever the derivative of the natural log is, that, it's a quotient. I don't want to have to deal with that. So we want to be able to expand this out. Remember your properties from the previous page. So ln of a over b is equal to ln of a minus ln of b. That we're going to use first. We've got the ln of a times b is equal to the ln of a plus b. ln a plus ln b. And then ln of a to the n is equal to n ln a. We're going to use those. That's the direction we're going to be going in. Let's do it. Oh, I know you're ready. I'm ready. Okay, so ln of stuff over stuff, we're using this. So that's going to be the ln of x squared minus the ln of x cubed minus 1. Now, I ask myself, is there any more simplifying I can do? There is with this, but not with that. And I'll get to this one in a second. This is ln a to the n. We're using this. That 2 can therefore come out front, just like this illustrates. So we'll get 2 ln x minus ln of x cubed minus 1. That's as expanded as we can make it. It's expanded as we can go because there's nothing else left in the argument. Here, even though there's an exponent, there's that minus 1. There's no ln rules at all that allow us to expand out something when you have addition or subtraction in this argument. All right, there's got to be multiplication or division. That's it. All right, very important. So we can't expand that further. We're done. This one, that cube root doesn't look good, so I'd get used to rewriting it like this. So I've got everything on the inside there, all raised to the 1/3. That's the cube root. The same kind of rewrite that we do with derivatives from the past, we're going to do again. Now that's ln of stuff to the n. ln of stuff to the n. The 1/3 is the n. It's going to come out front. 1/3 ln times x minus 5. Okay, what do we have here? We've got a times b essentially, right here. So we're going to add the ln's. You'll have 1/3 times everything, right? It's 1/3 times it all. ln of a, that's like your a, this is like your b, plus, because it's multiplication, ln of x minus 5. And that's it. You can leave the 1/3 out, or you can distribute it in. That's totally groovy. Plus 1/3 ln of x minus 5. That rocks too. And that's our final answer. Again, we cannot separate the x minus 5. That doesn't become division because it's not the ln of x minus the ln of 5. It's the ln of x minus 5. All right, let's keep reviewing. We don't have much more to review here, just 2 more pages. Like I said, 10 to 15 minutes of review. Here we're going to go the other way. We're going to condense. So now we're going to take the properties and we're going to go from ln a plus ln b and write that as ln of a times b. And we're going to go from ln of a over, just kidding, we're going to go the other way, ln of a minus ln b equals ln of a over ln of b. And then ln of a to the n is equal to n ln of a. Just going in the opposite direction. This is not as important this way in calculus, but there are some teachers out there that will test you on this in calculus. So just want to make sure it's there for you if you need it. So okay, we've got a lot going on here. Before we can condense, I always deal with the exponents first. You're dealing with the order of operations. You want to put exponents up first before we can deal with subtraction or addition. So ln x minus ln y squared, whoop, that comes up there. 1/3 comes up there for the z. So plus ln z to the 1/3. Oh, sweet. Now from here, I'm going to divide. I'm subtracting things here. So that's going to be ln of x over y squared. But we have plus ln of z to the 1/3. So we'd multiply that. Z to the 1/3. And if you feel it, you may certainly do this. X cubed root of z is the same as z to the 1/3 all over y squared. Nice. All right, let's keep rolling. Here we go. 1/2 ln x plus 2 minus all of that. We've got the exponents again to deal with. So I'm going to do ln of x plus 2 all raised to the 1/2. Nice. Minus ln of x minus 5 all to the 4th. Swinging the exponents erp. That's erp. That's right. Not up. Up with an r in the middle. Why not? Then we've got subtraction right here. So we're going to divide ln of stuff over ln of stuff. So that's ln of... Well, let's do it all in one fell swoop. X plus 2 to the 1/2 is the square root of x plus 2 all over x minus 5 to the 4th. Nice, 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 nice. And there's your answer. So just go step by step, cleaning it up. Some students like to do this all in their head, and that's fine if you've got that down. But again, the important part is being able to expand. That's where you're going to get big time dividends from putting in that investment of time. All right, last but not least in this killer quick brief review of natural log and, well, solving out equations now. So sometimes you're going to need to be able to solve out equations. It's going to come up in something called logarithmic differentiation. It's pretty gnarly. And a little bit later on when we get into differential equations, especially if you're in A, B, or BC calc, you're going to need it. Or if you're in an advanced calc class, you might need it. Okay, without further ado, how do I solve an exponential function? We need to undo 2 to the x equals 30. Now, I'm going to use the natural log here. You don't have to, but that's what I'm going to do. So I want to undo this. Logarithms, to me, allow me to play in the clouds, play with the exponents. So I will do the same thing to both sides. I'm going to take the natural log of both sides. Now, when I do that, notice that this x comes out front. X ln of 2 equals ln 30. And now from here, I can divide both sides by ln 2. As weird as that might look, think of this as a number times x. So if this was like 5x equals 20, you'd divide both sides by 5. It's essentially that, but with gross numbers. So I'm going to divide by ln 2, undoing the multiplication. On both sides, I must do the same operation. And that leaves me, this cancels, with x equals ln of 30 over ln of 2. Now, do not get confused. So that's your final answer, right? Whatever that is, as a decimal, doesn't matter, just leave it. We're going to leave our answers in logarithm form. Now, if your teacher tells you to round to the nearest whatever, then you use your calculator to plug this in. It's not bad. I want you to be able to do this without your calculator. Keep in mind this does not equal ln of 30 minus ln of 2, right? That is bad. And that's because this is not the ln of 30 over 2. This is the ln of 30 over the ln of 2. Two different things there. Two ln's, not one. All right, last but certainly not least, let's solve this one out. We'll add 5 to both sides. We're going to isolate e here. Add 5. Oh, yeah. That leaves us with e to the 3x equals 11. How do I undo e to the anything? The natural log. So I'll take the natural log of both sides. I'm going to show that in a separate step, just so later on if you're looking at this note, you're like, oh, okay, that's how we got from here to here. Don't want to mix too much up. ln of e, they undo each other. They're pure inverses. So that is completely gone. 3x remains. And that's equal to the ln of 11. Now, how do I isolate 3x equals a number? Ignore the ln of 11 on the right side. It's gross. It's nasty. I just divide by 3, right? Don't worry about the whatever the number is on this side. So if we divide both sides by 3, here we go. That cancels, and you're left with x equals, you could write that as 1/3 ln 11 or ln of 11, all of it divided by 3. To be very clear, this is not ln of 11 over 3, right? That is not the same thing. This is ln of 11, the number, and then divided by 3. That's it, y'all. A very quick review in almost exactly 15 minutes. How about that? I will see you in the calculus part of this. I can't wait. Peace.